Yeah, welcome to more polar coordinates. Want to finish what we were doing last time? Oops, this one. We're getting pretty far along, actually. Today we want to do calculus of polar coordinates. Well, I'll just remind you for to begin where we were at. We had said that in the plane, instead of identifying each point with its xy coordinates by dropping a perpendicular to the x and y axes, number lines, we can instead take the radial distance out, call that r, in which case r was the square root of x squared plus y squared by the Pythagorean theorem. Take the angle counterclockwise from the positive x-axis, call that theta. So that theta satisfied tangent theta equals y over x. Right? Moreover, we can let r be negative and take the opposite direction. Still, tangent theta would be y over x if you're in a direct opposite direction by trigonometry. And in that case, we take r to be negative the distance to this point, and we say still r squared equals x squared plus y squared holds. So these are nice transformation equations, either for using r positive or r negative. And then x and y have these conversion equations, right? If you drop the perpendicular, this side length has to be r cosine theta, so that this over this is cosine theta. This one has to be r sine theta, so that this over this is sine theta. And you get these equations converting back, and they turn out to work out if you do the negative r prescription also. So those were the two conversion equations we had for going back and forth from rectangular uh, to polar, in which case you had two choices for theta. You had to pick theta in the same quadrant if r was positive, or theta in the opposite quadrant if you chose r negative. So theta, same quadrant when r is positive, opposite quadrant of the original point if r is negative. If r is 0, it doesn't matter because all angles give the. All right, hopefully that looks familiar. Some equations, that's what we had right at the end. Maybe you've had some questions on the homework problem too. I don't know. If you do, I'd be interested to work on some of those. Here's an example of converting equations. We did a bunch of other things too, of course. Suppose I say convert to rectangular coordinates, right? And sketch. Uh, Maybe I have to erase this top, unfortunately. I wish I had a bigger board. Suppose I check r equals -3. What does that sketch? Anybody remember? Yeah, the number. It's a circle whose radius is the absolute value of this number. If you think about it, you can go at any arbitrary angle. It is arbitrary, right? It's not specified here. And then any angle, and then go 3 minutes the opposite direction. So it's all points 3 units from the origin opposite any angle sweeps out a circle of radius 3. So that's a nice way to think of it is as a number of circles. Oh, radius absolute. You want to keep that in mind. I like the intuition. You could rewrite this by converting it like this. You can say equivalently, this is r squared equals plus 9. Now you've got two solutions, minus 3, but the points you get by going one direction backing up 3 are the same as you go by taking all directions and going forward 3. And now you can see that this is just the equation. If you use r squared here, it's getting mixed up. Use this equation right here, we could call these 1 and 2. By 1 and x squared plus y squared equals 9 is the corresponding rectangular. one of these things you see over here in converting equations. When you convert r and theta, when you're given coordinates r and theta, you use these to get x and y. But when you convert equations, just use either, whichever is more convenient. So this time here, it was more convenient to use equations 1. But sometimes it's more convenient to use it. But there's the evidence radius 3 by converting it to rectangular coordinates too. So there's the sketch and there's the conversion. Then if we took theta equals a number like theta equals 4, what is that? Okay, that's a line. And if you think about it, here's the intuition. You want to have this. This is the number of radians. Pi radians is a straight angle. That's 3.14. You're almost a third of pi past there, so you're somewhere in here, your angle. And then you let r be arbitrary. Arbitrary positive r puts you out along this ray. R equals 0 puts you here. And r equals negative means you back up the opposite direction. So this is a line that has this polar origin. However, if you want to convert it, how would I convert that? I want to get something in this equation, right? So the way I can get that tangent of both sides and say tangent theta equals tangent 4. And then tangent theta can be replaced by y over x equals tangent 4. And I get the line through the origin y equals tangent 4, the number, times x. So it's a line of tangent 4 through the origin. How about that? Have to be careful on these though, because sometimes if you take the tangent of both sides, you well, tangent works okay here, but on some of these throwing out solutions or introducing new solutions. Oops. Let's put that one back. So it's a line of slope tangent 4. And there's 4 radians. Suppose we have this one. We had one like this last time, just to remind you. R equals 3 secant theta. What would I do with that? Yeah, I can rewrite that as R equals 3 over cosine theta, and then and theta. So I get, instead of r replacing with square root x squared plus y squared, I don't know how to replace secant theta, but if I do this, right, I'll rewrite it as r cosine theta equals 3. Now I can replace this with x and say this is x equals 3. It's just that line. However, you have to be careful, right? Because when I'm multiplying by cosine, theta x equals 2, and I multiply both sides by x, I've got x squared equals 2x, and now 0 is a solution. It wasn't before. So in some of these problems, be careful when you multiply through by something that could be 0. This one didn't introduce anything select. All right. Now some more here. Suppose I have this one. This is a real good example I like. R equals 2 cosine theta. And this one's easy to sketch, right? It's the vertical line. Equals 3 right there. What if I wanted to convert and sketch to cosine theta? What do I do? Hmm? Yeah, you multiply both sides by r because I've got r squared something in the transformation equation, or cosine theta. Now I can rewrite this one by equations 1, x squared plus y squared, and I can replace r cosine theta with x by equations 2. So I use both 1 and 2. Convert that. And now, right, I want to simplify that to sketch it. How can I simplify this? So we'll check it. Rewrite it this way: x squared minus 2x plus y squared equals 0. You complete the square. Ask, what do I need to make a square in x out of these terms? I take 1/2 of this number, right, and square it. So it's minus 1 squared is 1. Both sides, I have a square here. That's just what I add over there. Having added just one number, this is now x minus 1 squared plus y squared equals 1, which is a, yeah, a circle of, if you write this as 1 squared, a circle of radius 1 at 1, 0, right? So remember, x minus x naught squared plus y minus y naught squared equals r squared is the general equation for a circle. So it's a circle radius 1 at the point 1, 0. You just took the unit circle and translated it to 1 unit in x, placing x by x minus 1. So I sketched that quite nicely. Just put out here at 1, 0, circle radius 1. There it is. And then there's a good one here. This is a homework problem, I think. I forgot if it was D, was it? E. R equals 4 times sine theta plus cosine theta. What can I do with that one? I can distribute the 4, yeah. I'm going to do more than that. I'm going to try and get, instead of sine theta, I want r sine theta. Instead of cosine theta, I want r cosine theta. I'll just multiply through by r and get 4r sine theta, also distributed, as you said, plus 4r cosine theta. And now one thing I have to think about carefully. Right? So I have to think about sine equal to 0, right? If I choose equal 3 pi over 4, I can make sine theta equal square root 2 over 2 and cosine theta equal minus square root 2, which I make it 0. And then r equals 0 is a solution. So that will be the origin. And so when I multiply 2 by r here, I force the origin to be a solution because 0 equals 0 plus 0 by making r 0 alone. New solution can be 0 and theta can be any, but nonetheless, it's a complete set. So actually the same point set. We can say these are equivalent equations for points of the plane. Even though we've introduced new pairs of Mark solutions equals 0 theta equals 0 theta, but not this one. All right, so this is the same point set, and now I've got x squared plus y squared equals 4y plus 4x by the equation 1 and 1. To simplify it by completing the square again, I'm going to take x squared minus 4x plus y squared minus 4y equals 0. I'm going to add each of these things. So this is negative 2 squared is 4. So I need 4 there. Same thing here. I take 1/2 of this number and square it. Gives me 4 here. make it squared. Squares that these are, I've got x minus 2 squared is this one. It's always half of this number. Plus y minus 2 squared is this one. Equals 8. We can write that suggestively as square root of 8 squared. And we got what? Circle, right? Minus x naught squared plus y naught squared equals r squared. Circle of radius r. That one, x naught. The circle is now at 2, 2 of radius square root 8. So it goes like this. That's these points here. Circle is a part of the grid. It's just make the point. And the center is part of the. Yeah, well, you just have to try and convert them to something that's an equation 1 and equation 2 is the idea. Then we try converting the other way. This time I won't. The polar sketch it, so we'll just say convert. Sometimes it's simpler, however, to write down. Suppose I want to convert a line, right, a vertical line, y equals 7. How does that convert? Yeah, it's hard to hear still. Huh. Yeah, going this way, too. Sometimes you can save a step by using equation 1, but equation going this direction. The it's just a matter of sometimes you be a little quicker if you will say equations 1. So I'm just going to replace it straight out of equations 2 and just plug in. R sine theta was y by equations 2. There's an equation. So a lot of times they'll say right R is a function of theta because that's how we like to plot these things we said last time, right? So I'll write this as R equals 7 over sine theta equivalently, provided I be careful when sine theta is 0, there isn't any solution here. There isn't any solution here, so it actually checks out. You just have to think about it. R equals 7 cosecant theta. So there's the equation. R equals 7 cosecant theta. How about that? Horizontal line y equals 7. Some of these problems may not say write R as a function of theta. Just look, you just have to decide. In that case, they may just let you leave it like this. How about this one? 2x squared plus 2y squared minus 3 equals 0. How do I convert that one? Yeah, oh, you saw the easy way. I was going to do the hard way first. Good. Yeah, so going to factor out 2 from here, right? It is x squared plus y squared. This is what you want to do on here to save the most time. Instead of using equations 2 that always work, if you see an x squared plus y squared or a tangent y over or a y over x, you can convert them from equations 1 faster. So I'll rewrite this as 2r squared minus 3 equals 0. Evidently, r squared equals 3 halves, which we recall is circle, right? So here's an equation for that circle. You can also rewrite this as r equals square root of 3/2. Why can I do that? That'd be even easier. Actually, two solutions, right? R equals square root of 3/2 or r equals minus square root of 3/2. Why don't I put this? Answer is I can, but it's repetitive. This is the same circle, right? R equals a number is a circle with this radius. R equals a negative number is a circle with absolute value of this radius. It's the same circle. So I can leave that off and just say this one is R equals square root of 3/2. How about that? And then we'll make the following note. If you get messed up on these, you can always just use equations 2 when you're converting rectangular to polar, because you just do this. You can write 2x squared plus 2y squared minus 3 equals 0. It can be written as twice r cosine theta squared plus twice r sine theta squared, just directly substituting in minus 3 equals 0. The only thing you want to look for here is that you tend to get sine squared plus cosine squared. You want to make sure uh, you simplify that. So this now becomes 2r squared cosine squared plus 2r squared sine squared equals 3. I'll put on the other side. And now you see the 2r squared here multiplies cosine squared plus sine squared. So just look for this. If you do the direct transformation, you want to look for trig identities. Now this is 1. I've got 2r squared equals 3. Once again, r squared equals 3/2, or simpler, r equals square root of 3/2. Same point set, so I'll put equivalent, even if it's not the same solution set for r. All right, feel comfortable with those? Yes? I think it's not too bad on that section. The object now is to do calculus with these, right? Because there's lots of things that come up in polar coordinates that that come up in calculus that are simpler in polar coordinates, I was going to say. So the first one is going to be area. A simple polar region is what we're interested in finding the area of. There's lots of regions that are easy, but some of them are easier. It's a region like this. You're between one ray, theta equals a constant alpha, and another ray, theta equals a constant theta. And I told you, suppose we're inside a curve, r equals f of theta. And maybe we want to find this area. This would be nasty. This curve on top and bottom from here to here, finding the intersection. And then this curve like this. I think it's worth giving the proof on this. It shows you something that's useful in other applications about breaking up. So for this, I will describe it like this. It's 0 less than or equal to r less than or equal to f of theta, right? R and theta between these two angles. Alpha less than or equal to theta, less than or equal to theta. And something the book hasn't put on for some reason, but you really don't want beta to be more than 2 pi radians around. You start overlapping. So I'll say this is actually less than or equal to alpha plus 2 pi. You don't want to go more than once around. So that's a simple. And here's suppose I think like in calculus 1, here's a polar region again. Theta equals alpha, theta equals beta, r equals f of theta. And in order to find the area enclosed, I'm going to break this. Here's what we can increment theta. So this could be uh, at the angle alpha, I could call that also the angle theta 0, right? And if angle theta equals beta, I can also call this angle theta n. And I'm going to break it up into n sub-angles, right? So this will be theta 1, theta 2, theta dot dot dot. Theta n minus 1 will be that angle. And just polar coordinates. Anywhere in the middle, maybe this angle right here, which I'll call, since it's in the first increment of theta, I'll call it theta 1 star. At that angle, I will take the radius out to the curve that I'm trying to find the area inside of, this thing, and I'll take an arc of a circle and say, well, the area inside this slice of pizza, we call it of a circle, approximates the area inside the curve. And then in the second interval, I'll do the same thing. I'll take some angle theta 2 star, and I'll take the radius out to the curve here. Right, this radius is r of theta 2 star. This radius here was r of theta 1 star. And it's just like taking the height of a point. Now I'm taking the circle point. And so I add up these over the various intervals, these slices of pizza, and say, well, if I add up all of these, here's theta n star, some angle in the last increment. And I go out here and I estimate the area inside in here by an arc of a circle of the radius right here, the radius of r of m star. So instead of taking of rectangles, we take radius of add up the right? Area of a sector of a circle, right? A sector being a slice taken out of the circle between two angles at two central angles. This is an angle phi given in radians. What's the area inside the circle here? Remember that? Pretty easy. The area of the whole circle is pi r squared, right? And then you want this sector r squared phi. So this is the area. The area is 1/2 r squared phi. Now I've got it because I'm going to get rid of this. For the sectors we're interested in here, where the increment is between theta k minus 1 and theta k, or so this would be an angle theta k minus 1, and this would be an angle theta k. We can call this little increment delta theta k. Just instead of delta xk along the x-axis, we have delta theta k. The angle is theta k minus 1, the difference in angles. And then this would be delta theta k increment in the sector. Excuse me. So this is k sector. And now from our formula there, we know what its area is. AK, this area in the K sector, times the angle. Let's see, R is F of theta. Oh, I put R. Maybe I should put F here since I wrote F, huh? Call it F, I guess. That's the radius function, is F. Book used. All right, so this is 1/2 F of K star squared, right? 1/2 the radius squared of K circle. This radius is F of theta K star, intermediate point. 1/2 radius. For the enclosed area by adding up n of these. I just take this Riemann sum k equals 1 to n of AK, all the areas of the sectors, right? That gives me an answer. And then what happens? Take the limit of that as n goes to infinity. I'm going to define that to be the area. Why would I make that definition? If uh, if this function f of theta is continuous, it doesn't matter how you pick your increments here to make the partition, you get the same number. And so we want to, like the rectangle problem, we could use inscribed sectors, the smallest radius in each interval, and get a number. We could do circumscribed sectors, add all those up and get a number. And it would be the same number in the limit, right? You'd overestimate for any finite number of these in the one case. The limit, if they get and then this is the limit as the number of sectors goes to infinity of the sum k equals 1 to n. AK was this. F of read right. 1/2 F of you don't need this anymore. But from calculus 1, when we say limit as n goes to infinity of the sum f of xk star, a function of xk star, delta xk, k equals 1 to n, when we wrote integral a to b f of x dx, right? Replace dx in this. So we can rewrite this in that same notation. This is the function of xk star. And the limit sum becomes the integral sign. Delta theta k becomes d theta instead of dx, right? Because we're using theta instead of x. So by definition, we have here that this area is equal from the minimum theta to the maximum theta, that's just alpha to beta, 1/2 f of theta squared d theta. By definition, I like it more. So I'm going to do this. Instead, write r equals r of theta and get something that's more memorable to get, and I'll pull the 1/2 out. Area is 1/2 integral from alpha to beta, r of theta squared. So it's just r squared d theta. Look, it's 1/2 r squared d theta instead of 1/2 r squared theta. It's the old area of a sector, 1/2 r squared theta, except r is a function of theta. Instead of theta, you write d theta, the infinitesimal angle, if they like to call it. So it looks like the sector area formula with this integral sign in here and d theta instead of theta. I think it's easier to remember that way. So I'll put that one also, and I'll use that in my examples here. All right. That's the first formula. Let's do some problems like that. Part of the trouble is just figuring out get the right integral set up. Uh, find the area between these curves. R equals 2. I'm sorry, R equals 1/3 secant theta. Theta equals 0. And theta equals pi over 4. Using what does R equals 1/3 secant theta look like? Drawing this is real helpful, by the way. You don't have to sometimes, but it's still kind of nice to have a feeling. This becomes R cosine theta equals 1/3. Oh, it's x equals 1/3. It's just a vertical line. X equals 1/3. And so what I'm really doing here, I'm looking at the vertical line. We'll try this anyway. But see, that's the way you check your answer sometimes, if it's a simple region in rectangular coordinates. If we want to do it the hard way, then we're thinking of, maybe I better draw this bigger, huh? This is x equals 1/3, or r equals 1/3 secant theta. And then theta equals pi over 4. theta equals 0. And the advantage of drawing the picture is now you see, oh, it's between this ray, theta equals 0, and this ray, theta equals pi over 4. And between r equals 0 and r equals 1/3 secant theta, this must be my r of theta or f of theta, depending on your notation, right here. The outside curve between two constants and this outside curve. So I'll just say something, but too late now. Is 1/2 r squared theta with an integral sign, right? 1/2 r squared d theta, where r is a function of theta. Here's our formula we just wrote: 1/2 r squared d theta. And it goes from the minimum angle 0 to the maximum angle pi over 4 in the region, right? Well, I just have to take integral 1/2 the integral of 1/3 secant squared d theta. Well, that's not too bad, actually, right? Because what's the integral of secant squared? It's actually an easy one. We did all those hard integrals. You would have got this one before we did this, probably. What is an easy way to do? Well, let's give you. Yeah, it's just tangent. So I'll pull the 1/3 squared out of this 1/9 times 1/2 is 1/18. Integral secant squared theta d theta, and he's right. This is just the derivative of tangent, right? So I know this integral by heart from last semester. I have 1/18 tangent theta evaluated at 0 and pi over 4. Take the difference. 4 minus 0. Right? Remember tangent of so this is just 1/18 times 1 minus 0 is 1/18. How about that? Would have been easier for this. This is good practice. Uh, 1/3 squared is 1/9 times 1/2 is 1/18. Bunch of fractions. How are we doing on time here? Oh boy. Okay. Um, is that now you can do some interesting curves, not just these straight lines and stuff. There's stresses. So there's going to be special we're going to do next time that make this integration in polar coordinates real easy. R plus b cosine theta, or r equals a plus b sine theta, is called a limison, and it has a shape like this, or it can have a shape like this, or it can just be have a dimple. And these kind of curves